Okay, next one. Take a moment and read through problem number 2. I realize that this sounds familiar, but there actually is a reason we're taking a look at this one. We still have our river, and I've got my 3-sided fence over there. I'm going to say that's X, and that's Y, and that's X. The fence will enclose 56 square feet of land, but dimensions would require the least amount of fencing. So, first of all, am I trying to find a maximum or a minimum? Okay, least amount of fencing. I'm looking for a minimum here. And then, what am I trying to minimize? The area or the perimeter? Least amount of fencing, that's related to the perimeter. So my primary equation is going to be P equals 2x plus y. This is the thing that I want to minimize. Tell me what the secondary equation will be. If we're told the fence is going to enclose 56 square feet of land, I think my secondary equation can be xy equals 56. Well, let's solve this for y. We can make this y equals 56 over x. And then we're going to go and plug that in over here. My perimeter is going to equal 26 plus 56 over x, which might be easier to think about as p equals 2x plus 56x to the negative 1. I know that x has got to be greater than or equal to 0, but I actually don't know what the maximum is. If x is 56, y would be 1, that would work. But if x is like bigger than that, like 112, y would be 0.5, and if it's double that, 224, y is 0.25. I think I can just keep making x bigger and bigger and bigger. Y is going to get really small, but there's really no bound there, which is going to be a little bit of an issue. What we're going to do here is, instead of using our candidates test, we're going to use that other thing that I referred to called our global justification for an absolute max or an absolute min. This is going to look very similar to the work that we do to find a relative max or a relative min. There's just going to be a slight difference with our language at the end. If I was trying to find a relative max or min of this, you would need to find the derivative and then find your critical value or values. How about you take a moment and go do that? Find your derivative and then tell me what the critical values will be. Okay, so my derivative is p prime equals 2 minus 56x to the negative 2. Okay, so p prime equals 2 minus 56 over x squared. Should probably get a common denominator here. I'm going to multiply this by x squared over x squared and say 2x squared minus 56 over x squared. That denominator just gives me 0. But the numerator, let's see, 2x squared minus 56 equals 0. 2x squared equals 56. X squared equals 28. X equals plus or minus square root of 28. However, since x is a dimension, it doesn't make sense to say the length of the side is negative root 28, so we're just going to go with positive root 28. Or I suppose we could say 2 root 7. I'm going to do my number line as if I was doing a relative minimum. I'm going to put a tick mark at 2 root 7. I need to label my number line because I'm about to test my values in p prime. I think I'm going to go back to this version of p prime. If you plug 1 into p prime, is it positive or is it negative? I think plugging in 1 should give you 2 minus 56, definitely some negative number. Okay, root 28 is smaller than root 36, or 6. If you plug 6 in for x, that would be something in this region. Do we get p prime to be positive or negative? I think if we plug in 6, we're going to get positive. Negative, then positive. I've got a relative minimum at 2 root 7. But I can say a little bit more than that, because I only have one place where my sign is changing. Because I am decreasing everywhere before here and increasing everywhere after, this relative minimum has got to be my absolute minimum. Let me talk about that again. I'm decreasing everywhere before, increasing everywhere after. There's no way I can ever end up lower than at that x value of 2 root 7. And this is what's called my global justification. Let me write out what I just said. P has an absolute minimum at x equals 2 root 7 because I am decreasing everywhere before there and increasing everywhere after there. Because P is decreasing everywhere before x equals 2 root 7. How do I know that? Because p prime is negative and increasing everywhere after x equals 2 root 7. Because p prime is positive. And again, what I just wrote out over here is called our global justification. We're kind of talking about what is happening everywhere along our real number line. I would not be able to do something like this if I had another tick mark and then a negative sign there, because I'd be decreasing, then increasing, then decreasing, and I'd have no clue if this is my absolute min or if it goes lower than that somewhere else. But because there's only one place where I'm changing sign, and I'm decreasing everywhere before and increasing everywhere after, that's going to be my absolute minimum. Take a moment, make sure you get that copied down. Then, what dimensions do I have? Well, my dimensions are, I know my x is 2 root 7. We should find our y. Y equals 56 over 2 root 7. You know what, I bet we can clean that up. 56 over 2 root 7 is 28 over root 7. Gonna rationalize. Why not? 28 root 7 over 7. This becomes kind of nice. That's just 4 root 7. What are the dimensions of the land that I'm enclosing? 2 root 7 feet by 4 root 7 feet. When I do not have a domain that's a closed interval with bounds on either side, we can't use the candidates test. The only way we can try to justify an absolute max or min is by using this global justification. And for this to work, I'm really allowed only one critical value, and for my signs to change at that critical value, so I can say we're decreasing everywhere before and increasing everywhere after, or the opposite to justify an absolute max. We'll see this in a few other examples moving forward.